So I would like to thank the Italian Consulate in Houston, and in particular Dr. Cicchetti, for this opportunity. This afternoon, we are going to talk about the heavy metal remediation in the soil mine. So first of all, why we are still studying heavy metals? Because of the toxicity and the bioaccumulation and the consequences on our health, and where we can find heavy metals, generally speaking, in the biosphere. So it means water, soils, and rocks, and they could have a natural origin, but mainly an anthropogenic source. So it could be due to the industrial, mining, and agricultural activity. And this is the slide to show you how the concentration could affect our health, different organs. And this is a list of the maladies that they can cause. So they can affect lungs, liver, and also kidneys, but also they can cause the DNA damages, problem to hormones, the concentration of our hormones. So they are still a big problem. Other debate that is still open is if we can code this group of elements that you can see in red as heavy metals, or we can change their name as a potential toxic element. And there are a debate that is still open because some scientists suggest the change of this name instead of heavy metals as potential toxic elements, but other scientists suggest that also this name doesn't mean anything. So it's debate open. So we can, when we are speaking about heavy metals, so we are speaking about metals, metalloids and non-metals, and we can say that heavy metals means all the elements with the density over 5 grams per cubic centimeter, or when we compare the molar mass with the one from lanthanides and actinides. But we are not speaking about toxicity or bioavailability. First of all, one point we have to remember is that they are not always toxic, but it depends on the exposure and the concentration. So we have to think about their speciation, so the forms where we can find them, and their bioavailability. So the organs and the living organism, the amount they can incorporate. The other point is that they are non-biodegradable. So this is the problem due to the bioaccumulation, but most of them are hazardous or carcinogenic. Now, with these slides, I wanted to show you some characteristics of these metals and some picture of the minerals they can form with the other elements. And so we can find cadmium in batteries, pigment, and metal coatings. And remember that pigment is one of the points, the way that children can be affected by the presence of metals, because they can eat the paint from the wall. There are studies about the analysis of the blood for children and the amount of the metals that can be found on their blood. And these are a list of the sources, so mainly for cadmium is the mining operation. So this is the production of cadmium. The main producer is China, and then the main use is for nickel-cadmium batteries. Then we have copper, that is mainly used for communication, but also for construction with roofing and plumbing, and also for the alloys. And you can see it's for mining activity, metal production, wood production, and phosphate fertilizer production, where the main producer is Chile, and it's mainly used by the Asian country and for the equipment and building construction. Then we have lead, and for many years lead was used in the fossil fuels, and then it was banned, but then we can find industrial facilities in paint, ceramics, pipes and plumbing, ammunition, and there are many studies about the remediation of lead in the military area, and mainly it's due to the industrial activity. So we have the main producer, that is China, and mainly used in the batteries nowadays. Zinc is another method that is used for the galvanizing steel in rubber, ceramics, and paints. And then we have the mining activity is the main way that we can increase the concentration of zinc and purifying ores and steel production, but also for the coal burning or burning of waste. So you can see from these two diagrams how it is increased the concentration of zinc starting from 1960 to 2022, and China is the main producer. Then we have cobalt for alloys, the electroplating, paint, porcelain, ceramics, and so on. And mining activity is the main way that we can produce cobalt. The main country that can produce cobalt is the Democratic Republic of Congo, and mainly is used for the consumer devices or the electrical vehicles. Then the last one that I study is the nickel, with production used in the stainless steel for batteries, for alloy steel, for foundries, and due to also from volcanic activity, mainly by oil and coal combustion, nickel and metal refining, sewage, sludge incineration, manufacturing facilities. And nowadays China is the main producer, and it's mainly used for the stainless steel. So the idea is to starting from our idea to study phosphate for the immobilization of heavy metal, starting from this article from Iago in 1974. He studied the reaction between lead and phosphate, and as a product we have the precipitation of pyrophite, that is a mineral really stable in the environment. And so we decide to start from this reaction to understand if phosphate could be useful in immobilization of heavy metals in these particular soils, and if we can also analyze the mechanism for the immobilization and which type of phosphate we can use it, and if we can understand the amount of phosphate that we can use it to avoid also eutrophication phenomenon. So we started to study hydroxyapatite, that is a mineral stable. Mainly phosphate are stable to different environmental conditions. They show a low solubilities. Hydroxyapatite crystallizes in the hexagonal system, and these are the example of the 3D cell. And it's important to understand that generally the heavy metals that can be sorbed by phosphate can substitute calcium. Calcium has two positions, calcium 1 and calcium 2, and generally the metals could substitute calcium in the position 2. So we started to bought a synthetic hydroxyapatite from Alpha Ezer that was certified, and then we carried out some analysis to be sure about the composition, and this is an example of the XRD. And it's important to understand that XRD allows us to understand the type of minerals that we are studying in this case. Then we asked to the CF industries an example of the phosphate they are using. They produce fertilizer. They send us this fluorapatite, and we obviously characterize this fluorapatite with a chemical composition. This is the amount of phosphate in this type of fluorapatite, and this is some picture that we had from the atomic force microscope at Miami University in Ohio. Then we went to sample phosphate in Morocco. Morocco is the first country that can produce phosphate, and we sampled along the phosphate plateau, asking the permission to the company that is working in this area. And so we sampled two different type of phosphate, one that is a black one and the white one. The black one is, the color is due to the amount of the organic matter, and obviously we characterize this type of fluorapatite. We didn't use for this part of the study the white one because it has a low concentration of phosphate, and if you can observe the difference about the phosphate concentration between the Moroccan phosphate and the US apatite is really a low value. So then we start to sample soils from different ancient mine in south of Tuscany and southeast of Sardinia. And the mining activity is completely finished, like during the past century. These are the type of minerals that we can find in both of the areas. So we have pyrite, chalcopyrite, sphalerite, and galena. And mainly, if you can see, sphalerite in southeast of Sardinia is enriched with cadmium. These are the geology for the Tuscan activity. So we are in presence in, we sampled the area that's called colline metallifere. And these are the geology for the industrial and the mining Sardinian areas, that is close to the village called Alessia. So these are all the mines that we can find, and they are closed nowadays. So we started to create what we can define wastewater, starting from the Italian limit law for the amount of heavy metals that we can find in water, and also we can increase the concentration. So our concentration starts from 10 ppm to 500 ppm, with a contact time that is 2 hours till 48 hours. So then we decide about the amount of hydroxyapatite between 0.1 gram and 0.2 grams, and for the 2 fluorapatite only 1 gram. In this particular case, the amount of phosphate is not really high. We want to observe, to study if we can add later other phosphate, or if it is too high, this amount, to create problem to the environment with the eutrophication problem. And then we mixed all the 4 metals in other supernatant with the same amount of concentration, with time starting from 2 hours to 48 hours. And then we only used one amount for the hydroxyapatite and 1 gram for the fluorapatite from US and Morocco. And then we study the same phosphate for cobalt and nickel, but we increase the concentration from 100 ppm to 1000 ppm, and we increase the time from 2 hours to 3 weeks, but only for using as an amendment the hydroxyapatite with an amount of 0.2 grams. So after the filtration of this supernatant, we had the solid samples that we studied, first of all, with the XRD. Something that we observed, the first point, is that we don't observe the precipitation of hydroxypyromorphite. The other point is that we didn't observe a crystalline precipitation, but a poorly crystalline precipitation. And the other point is that we observed a decrease of the 8 peaks, in this case, meaning the dissolution of the hydroxyapatite. And the other point that is important to understand is that our samples, the soil sample, well overlapped with the XRD from the phosphate. So this is why we can say we don't have also the precipitation of hydroxypyromorphite. So then we studied the lattice parameter. And so we compared lattice parameter with the one from the our alpha acer hydroxyapatite, from the hydroxyapatite from the mineral powered diffraction file data book, and the hydroxypyromorphite, and then we plotted together. What we observed, without considering the difference if the solid material could have 1 contaminant or the 4 contaminant, because the behavior is the same. So we observed that our samples are close to the same lattice parameter for the hydroxyapatite from alpha acer, in this case, very far from the hydroxypyromorphite. We didn't observe a decrease in the A parameter, but a decreasing in the C parameter. So we suppose that we have the methods that could substitute the OH ions along the z-axis of the cell. And then we study our solid sample with infrared spectroscopy to understand the position of the different ions, again with the hydroxyapatite, and you can see they are quite similar. We observe this shoulder that is due to the presence of a poorly crystalline material, and this one here that is the POH group, in particular meaning that the metals could substitute this group, but then the other positions are quite similar. They don't show great difference. So then we study all the solid sample with the SEM EDS, and from EDS we can observe the presence of metals on the surface of phosphate. With the SEM we can observe the shape of the particles. In particular, we can say that we didn't see the paramorphite shape. Paramorphite has a needle shape, but we observe a quite circular shape, and we didn't observe also a difference in the shape before and after the contact with the metals, so we didn't observe the Oswald ripening phenomenon. Then we studied the solid sample with the atomic force microscope in Miami University, so we can observe, better distinguish the shape of these particles and measure the dimension of the particles to observe if there is a difference also with the dimension. Then we analyze all the supernatants with the ICP-IES, and in this case, we plotted time with the amount of the metals that can be immobilized. So we can say that 24 hours is the suitable time, and doesn't matter the initial concentration of the metals, but it's important to understand that only for zinc we observe a different behavior, because increasing the concentration, zinc is better immobilized, and we can explain this particular behavior, what we call the internal competition. So it means metals can compete among them and among the hydrogen ions to reach the site to be sorbed over the surface of the phosphate, and this is important to remember. Then we plotted together the amount of metals that could be immobilized with the pH. In this case, we have a concentration for the metals about 100 ppm. This is for the synthetic hydroxyapatite. They are well immobilized, it doesn't matter the time. Here we have the US apatite, and after 48 hours, metals could be well immobilized. This is the Moroccan phosphate, and 24 hours is the suitable time. But if we change the concentration, we observed how the US apatite, fluorapatite, is not really good as before, but it's better, the Moroccan phosphate. After 24 hours, we have a good immobilization of metals. And then we analyzed this phosphate for the immobilization of cobalt and nickel. So from 100 ppm to 1000 ppm as a concentration of the two elements, with a time between 2 hours and 3 weeks. And they show the same behavior. 24 hours is the best immobilization that we could have. So then, after all these studies, we start to study the sorption isotherms according to the Freundlich isotherm. So to understand the immobilization mechanism, and so the solute could be sorbed on the solid according to the Freundlich theory. So the isotherm is the ratio between the metal concentration at equilibrium and the metal concentration that is sorbed. And our sample have this shape that is a type L, a subtype 2, even though we could observe only for lead, it is only one contaminant, so only lead in the supernatant. We have another shape in few samples. It's a vertical one, meaning a cation ion exchange mechanism. In this case, the mechanism is completely different, but in the first part of that is a steep behavior, we have all the sites on the surface of phosphate that are free to sorb all the metals in the solution, reaching the concentration. we have reached the plateau, so it's quite the number of the site for desorption are decreasing. And this is valid for a solution where you can have only one contaminant or all the 4 contaminants. Then we study the molar ratio. The molar ratio is the ratio between the cation bound and the calcium release in the concentration. So we have few cases only when there's lead as only contaminant as an ion exchange mechanism, but mainly we have these 2 behaviors. So we have a value that is over 1, meaning a surface complexation mechanism, or a value lower than 1, it means a dissolution and the precipitation of a new phosphate mineral. But there are 2 points that we have to remember. First of all, when we have in solution different contaminants, each contaminant could choose different way to be immobilized to reach the phosphate. So it's not simple to understand the immobilization mechanism. And in particular, in our case, when you observed that the phosphate, after the contact with the metals, can precipitate with a shape equal to the original shape of the amendment, it's quite difficult to understand if you have the solution and precipitation mechanism. So then we went to the European synchrotron in Grenoble to analyze this behavior and to better understand if our hypothesis could be correct or no. So we analyzed our solid sample with the EXAFs, and in this case, we from the data that we get, we can say that we observed a fast complexation of metals on the surface of phosphate. So we designed a desorption mechanism, absorption process that could be divided in 2 steps. So we have a first rapid complexation on the specific site on surface of the phosphate, and then a diffusion into the phosphate structure, but with a non-crystalline precipitation. So at the end, we have a phosphate enriched with this metal and the release of calcium. And then we applied our phosphate to the Tuscan soil with a good result. And also for the Sardinian soil, we have the same good results. The other point is that we plot again our solid samples after characterize them with the XRD. So you can see soil, the XRD from the hydroxyfluorapatite and the fluorapatite from US, and they show the same behavior as the supernatant. And then in California, I analyzed the specific surface for the 2 phosphates, in particular from the hydroxyapatite, that is really an high value, and the fluorapatite from US show a low value. And this can explain why the fluorapatite from US can absorb less amount of metals compared to the Moroccan fluorapatite, because of the specific surface area. Then we applied this phosphate in an in situ case. In this case, we are in central Italy. The company is Nia Viscosa. They produce rayon. This site is closed nowadays. They don't produce anything more here, like in the half of the past century. And we sampled these materials that is enriched also with the other contaminant. So again, we used the phosphate that we used before, and also we used the white Moroccan fluorapatite with always the same behavior. So also from XRD, we have this shape, the same peak, and also from the analyzing the supernatants, we have a good result. So what we can say as the key points from this research is that we didn't observe the precipitation of pyromorphite. We have a precipitation of a poorly crystalline mineral. At the end, we have this calcium metal phosphate. From SEM, EDS, we can decide for 3 different mechanisms. So it's not really useful as a way to study these materials. From AFM, we can say that the type of phosphate could exert a control on the sorption process. And it's important to understand that changing the condition of the experiment, in this case, you can change the result, but the point is if we can immobilize metals. From the ICP-IS, we observed that the amount of phosphate at the equilibrium is low, so it means phosphate could be really stable. Also, if we change the condition of the pH in the environment. The other point is that it's not important the initial concentration, it's important the internal competition and the time. Time is fundamental. So generally speaking, we can say 24 hours are important to get a good immobilization for these metals. Then I moved to Germany and I started to study the phytoremediation. Phytoremediation is an old way to remediate soil and water, but the point is that you need plants that grow up in a short time and produce an high amount of biomass. Generally, the root system can absorb contaminants and then they can be transported to the shoot system. And then you can harvest and you have this contaminated biomass. The other problem is that, first of all, it's a technique that needs time. And then when scientists start to study phytoremediation, they observe that you need to stop this contaminated biomass. But nowadays it's changing. So you can use biomass for producing also electricity energy through the pyrolyzation. So it's really important in the case for the metal contamination, we can use the phytostabilization because it means we can reduce the erosion and runoff of metals. And it's important because the water can leach metals, it can transport metals in a different place, but also you can reduce the erosion of the soil because it means with erosion that the clay particles from soil can be transported at a long distance. Clay are the main particles that can bound heavy metals due to the cation exchange capacity, and also with this type of erosion, the fertility of the soil could be decreased. So phytostabilization is the technique, in this case, that could be useful to immobilize metals in soils and to clean also the water. It's possible to use for different type of contaminant, not only metals, but also the organic element or radionuclides. So this is one of the projects I'm working on. This is the mine in southeast of Sardinia called Monteponi. And these are a red hill due to the waste from the mining activity. These are called red mud. And you can see the title is from red to green because these particles could be transported by the wind. And southeast Sardinia is characterized by many days where the wind activity is really high. So the authorities suggest to the people to close the window to avoid to be in contact with these particles because they are really contaminated. And there's a village close to this mine because now the mining activity is finished. So the idea is to characterize all this red mud and to use phosphate and phytoremediation to immobilize metals. The other point, so we can increase the sustainability of this area, but also we can talk about circular economy because there's a study about to recover phosphate from municipal wastewater. So this is something that it's really important nowadays. This is the area of Monteponi, this red mud. It's really large and affecting the people that are living close to this old mine. The other area, this is another study from the Cathedral of St. John the Evangelist here in Lafayette. The point is that this study started from one of my past courses. Some students sampled the graveyards from this church. They found a high amount of arsenic. The origin is a geogenic origin, but it's possible to use phosphate and phytoremediation to reduce the mobility of the arsenic, in particular if it is an arsenic 5. If it is an arsenic 3+, phosphate means the remobilization of arsenic, so could be could precipitate as arsenate. The last project is to study the microplastic in soil, because it's increasing the presence of microplastic in soils, and then obviously vegetables could, and also crop could absorb microplastic. So it means we can eat microplastic. So thank you for the attention. And if there are questions, I'm try to answer to your question.